Hey guys, welcome back to my channel. So today we're going to cover an example of Newton's law of heating and cooling, and we're going to go through setting up the differential equation as well as solving the differential equation. So this is not going to assume any knowledge of identities other than the most basic knowledge of a very simplified version of Newton's law of heating and cooling. So thermodynamics people, don't come at me. This is for a Calc 2 introductory exploration of the topic, and there's definitely been a lot of simplifying assumptions made. So we're going to be working in single variables today, and the most basic Newton's law of heating and cooling would be that the rate of change of the temperature, so I like to use P for temperature over time, and we're going to assume that's equal to our constant of proportionality times the difference of the ambient temperature minus the temperature function. Okay, so there's our Newton's law of heating and cooling that we're going to be using today. Let's take a look at our example. So for our example, we're going to assume that a glass of milk is moved from a refrigerator with a temperature of 5 degrees Celsius. Let's highlight that. That's going to be relevant. To a room with a temperature of 20 degrees Celsius. 1 minute later, the milk has warmed to a temperature of 7 degrees Celsius. Again, I feel like that's going to be relevant. So we got 1 minute, temperature 7 degrees Celsius. After how many minutes does the milk have a temperature that is 90% of the ambient temperature? Okay, so obviously what we're going to want to be looking for is we need to know a moment of time for our solution, and specifically we want to know the time at which the milk reaches 90% of our ambient temperature. So we need to know what t value makes P of t, the temperature of our milk, equal to 90% of the ambient temperature. And the ambient temperature for this problem would be the temperature of the room. So when we're talking temperatures, you're always going to have the temperature of the object versus the ambient temperature in mind. So our object that we're measuring the temperature change of is the glass of milk. So our P of t is going to model the temperature of the glass of milk over time. The ambient temperature is going to be the room that has a temperature of 20 degrees Celsius. So we want to know, when is our P of t 90% of 20? Okay, so that would be $18. Okay, so that's our final goal, but obviously if we want to figure this out, we're going to need to have an equation for P of t. So that's what we'll go about solving. So let's set up our differential equation. So dp dt is going to be equal to K times, let's fill in our ambient temperature. The ambient temperature is the room temperature, we already said, so that would be 20 minus the temperature function for the milk, which would be P. And let's write our conditions down. So what's going to make this problem unique to this particular situation is going to be the starting temperature. So P of 0, the starting temperature of the milk, aka the initial condition, would be P of 0 equals, it looks like the milk starts at 5 degrees Celsius because it's coming from a fridge that was 5 degrees Celsius. And then P of 1 would be another condition that we'll find helpful. And it says that at P of 1, the milk has warmed to a temperature of 7 degrees Celsius. Okay, so those are our two conditions, and we'll use them when relevant. So at this point, we can actually start solving our differential equation, even without knowing what K is, and then we'll go on to solve for K later. So to solve this basic Newton's law of heating and cooling equation, really doesn't matter what constants we're filling in. The process is always going to be separation of variables. So every identity that the textbook or whatever you're looking at gives you is derived by using a separation of variables. So we'll move all of our p's to one side, all of our t's and constants to the other side. So when we do that, we get 1 over 20 minus p dp equals k times dt. And then we can integrate both sides. So we get KT plus our integration constant. Very important to remember that. Okay, a lot of people always ask me, is it necessary? Absolutely, definitely is. Okay, and then we get on this side negative ln of 20 minus p. Okay, so just give yourself a second to see where that came from. We used a u sub, and that's where the negative constant popped out from. So at this point, I like to divide both sides by -1 to give me ln 20 minus p equals negative kt minus c. And then raising both sides as the power of e, we get absolute value of 20 minus p equals e to the negative kt times e to the negative c. And at this point, I like to rename this constant d. So we would get d e to the negative kt equals the absolute value of 20 minus p. And then 20 minus p would be equal to plus or minus d e to the negative kt. And solving for p, we'd get okay, so there's our general solution for this problem, but we need to use our conditions to find our constants. So first we'll go ahead and we'll use the initial condition because that will help us determine what the constant in front of that exponential term is supposed to be. So at this stage, I kind of like to get rid of the whole minus or plus d because it comes out of the wash when we use our conditions. So I'll usually rename that as f at this point, and we'll figure out from our initial condition whether it's supposed to be positive or negative. So keeping in mind that our p of t is 20, kt, we'll use the initial condition, and we'll get that 5 should be equal to 20 plus f e to the 0, which would be 1. So it would mean that f should be negative 15. Okay, now we're going to go back to our solution curve and put that in. So our solution curve is now p of t is 20 minus 15 e to the negative kt. And now we'll use our second condition, which is that after 1 minute, the glass is warmed to 7 degrees Celsius. So plugging that in, 7 would be 20 minus 15 e to the negative k times 1. So 20 minus 15 e to the negative k would be 7. So just doing our algebra, we get 13 over 15 equals e to the negative k. To solve for that variable in the power of our exponent, we would take ln of both sides, and we'd get that negative k is equal to ln of 13 over 15. So k equals negative ln of 13 over 15. And using log rules, you could also write that as ln of 15 over 13. But it really doesn't matter because in the end, we're going to be taking our constant of proportionality and putting it back into our solution curve. So our solution curve is aka this is the temperature of the milk as a function of time. P of t equals 20 minus 15 e to the negative k. So that would be ln 13 over 15 t. So our solution curve, which is the temp of the milk, would be P of t equals 20 minus 15 e to the ln 13 over 15 t. And we always want to make sure before we move on that this makes sense. When we look at our solution curve, it does make sense because our ambient temperature is always going to be greater than the milk, which is warming in this problem. And as time goes on, this term means that the milk is going to be getting closer and closer to the ambient temperature of the room. As T approaches infinity, this curve approaches 20, the ambient temperature. Okay, so we haven't fully answered our question yet. Our question was, we want to know what T value is going to cause the milk to be 90% the ambient temperature. So we want to know what T value is going to make our P of T 20. So to solve that, we would set 18 equal to 20 minus 15 e to the ln 13 over 15 t. I'm taking the ln of both sides. Dividing both sides by our constant, ln of 13 over 15, we get that T is this ratio of logs. And before you get too hopeful, keep in mind that there's only 3 log rules. As much as it's tempting to think that there's more than 3 log rules to simplify, there's not a log rule that's going to give us any sort of simplification of a quotient of logs. So this is truly just the most simple exact version of T, and then you could use a calculator to get your decimal approximate. So let's go ahead and do that. Just out of curiosity, see what it would be. 2 over 15 divided by ln of 13 over 15. We get about 14.08. Okay, and thinking about our unit of time was given to us in, I believe, minutes. Yes, after how many minutes? And 1 was assumed to be a minute with our condition. So this would be 14.08 minutes. So in 14.08 minutes, our milk is going to be 90% of the ambient temperature. Hopefully this helped. See you next time.